Having successfully derived the first principle formula, not just that we derived it, but you notice that at every point in time, I gave a step-by-step detailed analysis of what happened that led to that formula. Especially in explaining the nonlinear graph. Quite interesting, isn't it? I want to believe that you understood the principle that was derived there. And of course, if you have any question, you can always feel free to send your question across and you get your response. It is now time we're going to apply the knowledge of what we learned from that first principle to solve our very first question we have here on the board. The question here reads, using first principle, show that if y is equal to mx plus c, then dy dx is equal to n, where n is the gradient and c is the intercept, and the intercept is actually a constant. Maybe you could think where this equation is going to be y equal to, say, 2x plus 3. Okay, so we're going to solve this question using the first principle. But I think before I go into that, right, let's take some water to calm our brains down after the long work in deriving the first principle. I hope you've taken yours, right? Okay, now let us move on to solve this problem using the knowledge of the first principle. It's really a simple one, huh? But let me quickly say this equation y equal to mx plus c is called the equation of a straight line in slope-intercept form. This is the general equation of a straight line in slope-intercept form. So take note of that. You have to memorize it in case anybody asks you any day, what's the equation of a straight line in slope-intercept form? Y equal to mx plus c. We are to prove, not show, simply means prove, that if you have this equation, dy dx, that is checking the way changes in x affect y, is going to be equal to n. That's what we are trying to establish. So what do we do? Just like we learned from first principle. You know that any change in x will affect y, will produce a corresponding change in y. And so we can choose to use delta x as usual to represent a change in x, and that will produce a change in y, which we're going to use delta y to represent. And we are going to add these changes to the two variables. So coming to the left hand side, I'm going to have y plus delta y equal to, coming to the right hand side, I will have m. Take note that the change is affecting x, not the coefficient of x, not what is multiplying x. The change is affecting the variable x and y only. Therefore, I'm going to open bracket, then x plus delta x, then plus c. Please take note, do not add delta x directly to this n. It has nothing to do with n. This delta x is a change in what? In x. Take note of that. Therefore, don't do this. Don't do this. Mx plus delta x, please. It's wrong. The change is affecting the variable. Okay, now from here we're going to make delta y subject of the formula, because our aim to obtain dy dx, we would have to get it from delta y over delta x. So making delta y subject of the formula here, I'm going to move y to the right hand side of the equation. So this is n, open bracket, x plus delta x, then plus c. If y crosses to the right hand side, it's going to become minus y. And then we can proceed to write delta y equal to n, open bracket, x plus delta x, then plus c. Take note, minus this y has a value. And what's the value of y? Just like in deriving the first principle, you remember, y is equal to f of x. That is a function that depends on x. Y is a function, a variable that depends on what? X. Which was written as y equal to f of x. The same thing here in this problem, y is a variable that depends on x here, and is given by this expression mx plus c. So in place of this y, I'm going to substitute mx plus c. I'm going to open a bracket for that, and then put mx plus c. All these terms represent what? Y. Now, I can work out this right hand side of the equation to see what I'm going to get before I start thinking of how to get delta y over delta x. Let's simplify the right hand side. So that's going to give us delta y equal to, coming to the right hand side, I can open up this bracket. If you do so, it's going to be m times x, which is mx, and then you multiply m by delta x, which is going to be plus m times delta x, then plus c. Alright, I've opened up that bracket. I'll also open up this bracket here. This negative will multiply the terms in the bracket. That's going to give us minus mx, and then this negative also affecting this plus c will change to minus c. Does that make sense? Simplifying this further, you would see clearly that we have mx minus mx. They are like terms, so they can go off. This will go off with this. You also observe that we have plus c minus c. That will also go off. I am left with delta y equal to n delta x. At this point, I've done my simplification of the right hand side. I will now convert this to delta y over delta x. And how do I get my over delta x to this equation? Delta y over delta x is simply to divide both sides of the equation by delta x. Divide through by delta x. Doing that, I have delta y over delta x equal to m delta x over delta x. Alright? Now, you notice that this delta x will cancel out this delta x, divide it, and I'll be left with delta y over delta x being equal to n. We're getting something nice. At this point, we'll take our limit. We'll take our what? Limit as delta x approaches 0. Of course, you know when you take limit as delta x approaches 0, that gives you your dy dx, your gradients. So we write dy dx is equal to limit of whatever the right hand side is. Limit of whatever the right hand side is, and the right hand side is n, as delta x tends to 0. And the limit of a constant, that is one property of limit. This n now is a constant, like a number. The limit of a constant as a particular quantity tends to any value will still give you that constant. Let me assume that I said, okay, fine, limit of, let's say limit of 2 as x tends to, let's say, 1. The answer will still be equal to that number 2. Therefore, limit of n as delta x tends to 0 will still give us what? N. This is equal to n. Therefore, dy over dx, that is dy dx, that's how we pronounce it, dy dx is equal to n. And the proof has been done. Alright? So this is how we show that dy dx is equal to m, our gradient. We are going to move on to the second question, but I hope you understand this proof. If you have any problem, you can rewatch this video lesson once again. But if you still don't find a solution to your problem, you can send us a question. Let's move on to our second question. In our second question here, we have this diagram. And the question reads, in the figure above, at what rate is y changing with respect to x at point P using the first principle? Please take note, WRT is the abbreviation for with respect to. This is the diagram, right? We have a curve. The curve is given by this equation, y equal to 2x squared plus 5. Now we have point P and point Q, and of course the value of x1, x2, the value of y1, y2. So it is required that we find the rate at which y changes with respect to x at a particular point on the curve, and the point is point P. Please take note, you could have been asked to find the rate at which y changes with respect to x at point Q. And I'm going to tell you this, the rate at which y will change with respect to x at point P will be different from the rate at which it will change with respect to x at point Q. That is why when we derived the first principle, I told you that depending on the point you draw the tangent to that curve, you will get different gradient value. You will get different values at which the dependent variable, in this case y, changes with respect to x. Alright, let's go straight ahead and solve this question. At what rates? When we talk about rates, differentiation is what measures it. Differential calculus. So dy dx is simply the rate at which something changes with respect to another one. Now looking at this, let me just make a quick sketch, although it's not absolutely necessary. This is what was given to me. Now I have something like this, like the curve. Alright, I have something like this, like the curve. And then we have these points, say point P. This is the point at which I am expected to find the rates of change of y with respect to x. Now I can just take my tangent through it. Are you seeing that, right? This is the tangent. And so this tangent will help me to actually get the rate of change of y with respect to x. So just a sketch. Are you following, right? Now how do we go about that? For us to get this tangent, if you look at this is points P and Q. If you join these points P and Q with a straight line, you will get a secant. For example, if this were to be point P, okay, point Q rather, this is point P, and then if this were to be point Q, if you join both of them, you are going to get a secant. You see that, right? A secant, because this passed through the curve, and you can see the space enclosed by the curve. Now, our aim is to see how we can change this secant to tangent. And of course, to do that, there's going to be a change in x and a change in y. Q will have to be moved down till it gets to point P. When point Q and point P meet at this point P, then you have gotten your tangent. And that will help you to find the rate at which y changes with respect to x. Like I said, this is just a sketch for you to get the idea of this problem. Are you following? We have a secant. If you join these points, secant, now the secant cannot describe correctly how y changes with respect to x. So you need to get a tangent through the point that you were asked the question. Let us now solve this. The function given to me, the equation of the curve, is y equal to 2x squared plus 5. And so both x and y will change. We're going to add delta x and delta y to x and y respectively. So this is y plus delta y equal to 2 brackets. Now you see this, the multiplier of this x squared is 2. What is changing is x, not that 2. So to this x, I am going to add delta x to it. This x is squared. So I will enclose this x plus delta x in bracket, and then I will square it. Plus 5. Now these are the changes, alright, in x and in y. I'm going to make delta y subject of the formula. So this is going to be 2 bracket x plus delta x. You square it. And then plus 5. Of course, this y will be taken to the right hand side, minus y. Delta y will now be equal to 2 bracket x plus delta x. You square it plus 5, then minus open bracket. Now you have minus y here, and in the question you know that y is equal to 2x squared plus 5. Look at it, the equation of the curve. So I'm going to substitute it. In place of y, we have 2x squared plus 5. Simplifying this further, this is delta y equal to, you open up this bracket. To do that, you have 2 brackets. This squared will be worked out first. If you have x plus delta x all raised to power 2, it's the same as x plus delta x in bracket, then multiply by x plus another delta x. I'm going to expand this. You can do this expansion yourself, and you'll get this same result. X raised to power 2, then plus, you multiply this x and this delta x, and then multiply by this 2, that is 2x delta x. And then plus this delta x, you raise it to power 2, which is going to be delta x all raised to power 2. Then plus 5. Come over to this, you can open up the bracket, you have minus 2x squared, and then minus 5. Delta y will now be 2x squared. I'm opening up this bracket with these 2 now, plus 4x delta x. plus 2 delta squared x, alright? That is a delta x squared or squared delta x. Then plus 5 minus 2 squared x minus 5. I've done the expansion, and further simplification of this would give us the following. You notice that this is 2 squared x. It will go off with this minus 2 squared x. It will go off, plus 5 will go off with minus 5. Having done that, this will be delta y equal to 4x delta x plus 2 squared delta x. Squared delta x. This is just like maybe in bracket and then you square it. Is that okay? Please don't think that this square is just affecting this x. Together, delta x squared. At this point, I've simplified the right hand side, and this is what I have now. I will now divide through by delta x. So this gives us delta y over delta x equal to 4x delta x, you divide it by delta x, plus 2 delta squared x, you divide it by delta x. You know, dividing all these things together by delta x is the same as dividing this one by delta x and dividing this one by delta x because of this plus. If I have, let us say, x plus y all over 2, even if this is minus, you'll get it as x over 2 plus y over 2. If it is minus, then it will be minus y over 2. So you see that division splits over addition. Are you getting me right? Division splits over what? Addition and subtraction. Okay, so this is what I'm going to get. Then if you observe this, you will notice that this delta x will cancel out this delta x. And of course, this is squared delta x. This squared delta x is just like writing delta x times delta x. That's the meaning of that. Therefore, one of it will cancel out the denominator. Alright, and to do that, I'll cancel this, then I'll just cancel this square. So that only one delta x will be left here multiplied by 2. And so we have delta y over delta x equal to 4x plus 2 delta x. Now that I've done this division, now that I have cleared delta x from the denominator on the right hand side, now take note of this. Anytime you are done with your simplification, and on the right hand side, of course, you know, you are able to clear delta x from the denominator, you can now take your limit. You can now do what? Take your limit as delta x tends to 0. Because there is no delta x in the denominator again, you can take your what? Limit in order to get your dy dx. Remember, dy dx is equal to the limit of the right hand side as delta x approaches 0. This equation you see here on the board is the second equation. This equation describes this second that I drew with black marker here. I'm sorry that these things are not straight, you know, I used freehand. This is point PQ. And joining this point PQ is a second. I explained that already. Getting our tangent, which is what we are interested in order to get the rate at which y changes with respect to x. These 2 points on the curve must meet. And when they meet at this point P, because that is where this question is based on, what we will get is this tangent. I use blue marker to show it. So this equation we got here is for the secant. How does the secant change to tangent? That is what now brings in the concept of dy dx. And we know that dy dx is equal to the limit of this whole term, 4x plus 2 delta x, as delta x approaches 0. So dy dx will now be equal to, come over here, all you do is, wherever you see delta x, substitute 0 in it. That's the implication. Is that okay? So this becomes 4x plus 2. This is delta x, so you put 0. 2 times 0 gives you 0. This is equal to 4x plus 0. Therefore, we have obtained that dy dx is equal to 4x. Now, we are told to find the rate at which y changes with respect to x at point P. If you look at our final value for the tangent, for the gradient, we have 4x. This occurs at a point, which is point what? P. Our final result of dy dx has x in it. Since this rate of change is to be obtained at point P, we need to get the initial value of x there. And the initial value, that is x1 value, is 1.5. So I'm going to indicate something here. At point P, x is equal to 1.5. You can see that clearly. Look at that. X is equal to what? 1.5. So, the rate at which y changes in respect to x, which is dy dx, will now be equal to 4 bracket 1.5. Just substitute the value of x into this result you got for dy dx. And then dy dx will now be equal to 6. And this is our final answer. This is the rate at which y changes with respect to what? X. Is that clear? For every change in x, y will be 6 times of it. Just much of the implication. We are done with this problem. All this analysis is just for you to understand what I've done there. I could have just started solving directly from here and not even bother you about this sketch. Let us move on to the third question and see how we'll apply this first principle once again. But you know, this third question I'm going to solve, I will use the formula directly. I've been able to solve from the beginning, from the foundation to get our final answer. The third question we're going to solve, I'll just get straight on to using the first principle formula directly to obtain our rate of change, to obtain our gradient, our tangent, our dy dx. We are moving on to question number 3. Let's see how we can handle this problem. It's about the heat that a car gives off, which is a function of the car's position. Generally, we know if you have a car parked at a particular place, depending on the temperature of that place, the car would usually give off heat. You know that. The car will heat up. So, we want to study the relationship between the heat that the car gives off and the position of the car. Of course, if the car is in a cold environment, it will be cold, you know that. It will give off less heat. But if you park it in a place where it's exposed to sun, for example, what's going to happen? It gets hot, giving off heat. So I want to study that relationship. Remember I told you calculus deals with how things change in real life. Let's go. The heat, H, given off by a car as a function of the car's position, P, is giving us H equal to 2P raised to the power 3 minus 10. Obtain the differential coefficient of the heat with respect to the car's position. At what rate will heat be given off if P is equal to 1? That is, if the car's position is equal to 1. So how do we go about this? From the question, what we have is that H is equal to 2P raised to the power 3 minus 10. This H now is a function of position. Heat is a function of position. So we usually write it this way, just like you've been saying for question 1 and 2, y equal to something about x. We can simply decide to write maybe y of x equal to, then we now write the expression that represents it. So the same thing here. Heat is a function of P. And according to the question, it is equal to 2P to the power of 3 minus 10. Good. You now see that this question is not about y and x anymore, like I told you when I derived the first principle for you. It's not always you see y and x. This y and x actually represent real things in real life situation. In this case now, our y, which is the dependent variable is our h, the heat given off by the car. And then p represents x. P is the independent variable, the position on which the heat that will be given off by the car depends on. So you get that right? Here, our P represents X, and H, the dependent variable, represents Y. Now I'm going to solve this question using the first principle formula. We know from first principle, we have that dy dx is equal to the limit of f of x plus delta x, then minus f of x. Now I'm going to divide all of them by delta x, given that delta x its value is approaching 0, tends to 0. And so we're going to rewrite this formula now in terms of h and p. So of course, you know that here h now represents what? Y. So it's going to be dh, and then x is our p in this case, dh dp. It implies that our dh dp will be equal to, we take the limit of the function f of p plus delta p, then minus f of p, of course, divided by delta p as delta p tends to 0. This is going to be the first principle formula using the variables given to us in this question, which is h and p. Let us now substitute and solve to get the rates at which the heat will be given off by the car as a function of position. This is dh dp equal to limit as delta p tends to 0 of f of p plus delta p. How do we get that function of p plus delta p? It's simple. It means we should come to the problem given to us, the function. Wherever we see p, we are going to add delta p to it. So in this case, this is 2p raised to the power 3 minus 10. So in place of this p, put p plus what? Delta p. Anything that happens to p in the given function, the same thing will happen to that p plus delta p. Going by that, I will write 2, then open brackets. This p will now be replaced with p plus delta p. Of course, this p is raised to the power 3, so you raise this to power 3. And then next, you have minus 10. Minus 10. Good. I'm done with that first part of f of p plus delta p. How you get it is simple. Go to the function given to you. Wherever you see p in the function, just remove that p. Replace it with p plus delta p. Then you see raised to the power 3. Every other thing remains the same. So coming over to this is minus f of p. And what is our f of p? Again, go to the function given to you. Wherever you see p, put p there. Now this is p. So in place of this p, you still put p. That's the meaning of this. This simply means go to the function. Wherever you see p, put p. This one means go to the function. Wherever you see p, replace it with p plus delta p. So coming to this is the function. I'm going to write it 2. It has to be enclosed in bracket. Then in place of this p, I'll fix this p there. And then it will be raised to the power 3 minus 10. I'm going to divide all of this by delta p. Now what is left is just to simplify. I'm going to open up these brackets. Let's see what this is going to be. Limit as delta p approaches 0 tends to 0 will now give us, we have this bracket, and then 2, open this bracket again. Let us expand this and see p plus delta p all raised to the power 3 is the same as p plus delta p in bracket times p plus delta p in bracket times p plus delta p in brackets. And then how do you get it? Please, I want to be fast using binomial expansion to get it. You can do your own normal multiplication. Multiply out these 3 brackets. In one of our classes, I'll show you how I use binomial expansion to get this quickly without bothering yourself about multiplying out the 3 brackets. So we go. First of all, the starting point will be this p, this first 10 raised to the power given to you here, which is p raised to the power 3. Does that make sense? Then plus the next 10, you are going to multiply this p by this delta p. But one thing is that the power of this p will now reduce from 3 to power 2. And then this delta p will now have power 1. You see, in this case of p raised to the power 3, why there is no delta p there? The reason why there is no delta p is because delta p in this case is raised to the power 0 when this p is power 3. Are you following? So in the second case, what I'm trying to say here is this. Multiply this p by delta p. The power of p will now reduce from 3 to 2. Is that okay? Then how do we get the coefficient? The coefficient in this case will be 3. Here the coefficient is 1. How do I get the 3? Simple. It's going to be this power 3. Use it to multiply the coefficient. You get 3 times 1. Then divide it by 1. 3 divided by 1 will give you 3. Why did we divide by 1? We just have only one term here. Only one term. So if I do this 3 times 1, giving me 3, I'll divide it by that one term, 1, which is 3. So the coefficient of the second term here will be 3. Then I'll multiply this p by delta p like I said. But the power of this p will now reduce to 2. Then delta p will increase from 0 here to 1. And anything raised to power 1 is that term. Anything raised to power 0 is 1. 1 times p raised to power 3 remains this p raised to power 3. That is why the delta p did not show here. We move on. Plus, let's move to the third term. In the third term, we are going to again multiply this p by delta p. The two terms we're trying to expand. But again, the power of this p will reduce from 2 to 1. And then the power of this delta p will increase from power 1 to power 2. But how do we get the coefficient that will multiply that product? Come to this second term now. Use the power of p to multiply its coefficients. 2 times 3 will give you 6. 6 divided by 2 because you have gotten two terms already. 6 divided by 2 will give us 3. So the coefficient here is 3. Multiply by this p, the power reduced to 1. Then times delta p, the power will increase to 2. Plus the next term. The next term is obtained by multiplying this p times delta p. But this p will now become power 0 there. I know p raised to power 0 will give you 1. Then delta p, the power will now become raised to power 3 in this term. And once this power of this p becomes 0, and then delta p now has power 3, which is the highest power of the expansion, it means you have finished with the expansion. Doing that, in fact, the last time the coefficient is 1. So it's going to be 1 times p raised to power 0 times delta p raised to power 3. And if you do that, it's simply delta p raised to power 3. I'm done with the expansion anyway. So this is going to be minus 10. Minus 10. Alright. Now, I'm done with this. 2. Look at it. P plus delta p all raised to power 3. I've expanded it. And then this is minus 10. Look at it. The next term now is this minus 2p raised to power 3 minus 10. So let me put that here. Minus 2p. Let me open up the bracket once from there. 2p cubed. Then plus 10. Yes. If this minus opens up this bracket, this becomes minus, and this will change to what? Plus. Divide all this term by delta p. Now, let's move on and see what we're going to get here. But at this stage, please, I would like you to open up this bracket yourself. Use these two to multiply each term here. Are you following, right? Because I'm not going to show that. I'll simply work that out, and then we see terms that can cancel off. Looking at this clearly, this minus 10 will cancel this plus 10, you know that. They are like terms. Then if you open up this bracket with these 2, 2 times p raised to power 3 will give you 2p raised to power 3. And here you have minus 2p raised to power 3, they are like terms, so they will cancel out. This minus 2p raised to power 3, and then this p raised to power 3 will cancel because these two will multiply it. What are you now left with? We'll be left with limit delta p tends to 0, 2 times 6, 2 times 3, p raised to power 2 times delta p will give us 6 p raised to power 2 times delta p, and then plus, we're going to use this 2 to multiply this 3p delta p raised to power 2 to give us 6p delta p raised to power 2. Use it again to multiply delta p raised to power 3. You get 2 times delta p to the power of 3. Divide this by delta p. At this point, I am going to split this division sign over each of these terms. You know that division distributes over subtraction and addition. Doing that, we have limit as delta p tends to 0. Coming here, this becomes 6p raised to power 2 delta p divided by delta p plus 6p times delta p raised to power 2 divided by delta p, and then plus 2 delta p raised to power 3 divided by delta p. Let's divide terms and see. This delta p will cancel this delta p, you know. This delta p will cancel 1 from this numerator of delta p, so this 2 goes off. Then this delta p will cancel 1 from here, so this will become minus 1. Let me cancel this and write power 2 there. Let me cancel it and write power 2. That's good. Bringing this out, this is equal to limit as delta p tends to 0 as delta p approaches 0. You know, that's what is going to give us our tangent from secant. Good. Now this is going to be 6p raised to power 2 plus 6p times delta p plus 2 times delta p raised to power 2. Now what do you do here? You are going to substitute the value of delta p to wherever you see your delta p. It is at this point we take the limit. That limit is putting the value of delta p into this. Are you following, right? By substituting the value of delta p wherever you see it. Our dh, dp, dH dP will now be equal to, come over here, 6p raised to the power 2 plus 6 times p times delta p, which is 0, plus 2 times delta p, which is 0 raised to the power 2. Now, working out this part will give us 0 already. This one will also give us 0. So you see clearly that dH dP will be equal to 6p raised to the power 2. So you see that the differential coefficient dH dP is equal to 6p raised to the power 2. It is the differential coefficient of the heat with respect to the cast position we are asked to find. This is the answer. We are done with the first part. Now, I'm going to conclude the second part here. In the second part, we are asked at what rate will heat be given off if the position of the car is at point 1, position 1, okay? So all we now need to do is simply say at P equal to 1, we are going to have that dH dP will now be equal to, remember we had it to be 6p raised to the power 2. So in place of this p, we are going to fix 1. It becomes 6 bracket 1 raised to the power of what? 2. In conclusion, dH dP at that p equal to 1, the answer is equal to 6. If you work out this, you're going to get 6. 1 raised to the power 2 will give you 1, then times 6 will give you that 6. And this is how we solve this. So it means when you park the car at position 1, are you following, right? Then you are going to get that the heat, the rate at which the heat will be given off will be 6 times whatever the change of the position is. That's what we have there. If the position is at, let's say, position 5, this will become 5 raised to the power 2, which is 25. You multiply by 6. And 25 times 6 is going to give us there about 150 or so. We've done a great job on this first principle of solved problem where I started it from step 1 down to the end. And in this question number 3, I've solved it using the first principle formula directly. I did not start from the basis to start deriving it. You want to watch this video lesson again and again. If you have any question, you can rewatch it. Maybe your answer is there in the video lesson. But if you think that you could not find your answer there, always, you know what to do. Send your question to us and you get your response. In our next class, I'm going to take you more on the application of first principle. We're going to use the first principle to solve some more questions. Until then, take very good care of yourself. Make sure you take your studies seriously on calculus. Bye-bye.